Okay, let's jump right in. The paper we're covering today is called RRL, Online RL Fine-Tuning for Flow-Based Vision Language Action Models.
Yeah, this one's pretty significant. It tackles a really persistent problem in robotics policy learning.
Right, specifically for those high-performing vision language action models, the VLAs like Puss and Tears, these are flow-based models.
Exactly. And that flow-based part was the kicker. Standard RL methods, especially policy gradient ones, need this thing called the action log likelihood. But for these models, because of how they generate actions using a deterministic flow, well, calculating that log likelihood was basically intractable, couldn't do it reliably.
So you couldn't easily use powerful RL algorithms like PPO to fine-tune them with real environment interaction.
Precisely. Until RL came along, this is the first open source framework designed specifically to get around that problem for these flow models.
And they introduced two main technical ideas to do it, right? Flow noise and Flow-SDE.
That's the core of it. Two clever ways to engineer things so you can compute that exact log likelihood needed for stable RL.
And the results, they weren't small improvements, were they?
Not at all. We're talking huge jumps. Like on the Libero long benchmark, which is known for being tough, Euro went from about 44% success rate after just one shot SFT.
Which is pretty low.
Right, very shaky. And char RL boosted up to 94%.
Wow, okay. That's a massive difference.
And it scaled too. On ManiSkill Multitask, which has like thousands of task variations, we went from around 41–42% success up to almost 86%.
So this really unlocks online RL for these specific but very powerful types of models.
Absolutely. It connects the dots between these great flow-based architectures and the generalization power you get from RL's active learning.
Okay, let's maybe take a step back for context.
Yeah.
Why was a whole new framework needed? What's special about these flow models and VLAs?
Right. So VLAs like the Pay series or others like Octo and RT, they're kind of the bridge, you know? They take in multiple types of input sensor data, maybe camera images, and natural language commands like pick up the red block.
And they translate that high-level instruction into low-level continuous movements for the robot arm.
Exactly. They connect the thinking part with the doing part.
And the standard way to train these has been pre-training on vast data sets, then supervised fine-tuning, or SFT.
Yeah, SFT uses demonstrations from experts. You show the robot how to do the task correctly many times.
But the paper highlights some big problems with relying only on SFT.
Oh, definitely. Two main things. First, getting that expert data. It's super time-consuming and expensive. You need perfect or near-perfect trajectories.
And second?
Second, the models can just learn to mimic or overfit the specific demonstrations. They might look good on tasks they've seen, but struggle when things change even slightly or when facing a totally new situation. They lack robustness.
Which is where reinforcement learning comes in. That's the third step, pre-train.
Yeah.
SFT, then RL.
Right. RL lets the agent actually interact with the environment, try things out, learn from success and failure. That's how you get better generalization and adaptability.
But we hit that wall again with the P-series models because they are flow-based. Can you break down what that means and why it was a barrier for RL?
Sure. So instead of just like spitting out an action in one go, flow models work differently. They start with random noise and iteratively refine it step by step, following a path defined by a learned velocity field.
It's like they're solving a differential equation, an ODE, to transform noise into the final continuous action.
Exactly. They model the flow from a simple noise distribution to the complex distribution of valid actions. But the key issue for RL is that this standard ODE solving process is deterministic.
Meaning for the same starting noise and state, you always get the exact same final action.
Precisely. And that's the problem for policy gradient methods like PPO.
Why is determinism bad for PPO?
Because PPO needs to estimate the probability of taking a specific action in a given state, the log likelihood, log PAS. It uses this probability to figure out how to update the policy, usually by comparing the likelihood under the new policy versus the old one.
Okay. If the action generation is deterministic, there's no real probability distribution over actions to work with. The probability is like 1 for one action and 0 for all others.
Sort of, yeah. It makes calculating a usable gradient for the log likelihood intractable. You can't nudge the probabilities if they aren't really there in a continuous sense. The math breaks down.
So RL had to find a way to introduce some controlled randomness or stochasticity into that deterministic flow process, specifically for training.
Exactly. And they needed to do it in a way that still allowed them to calculate a proper, mathematically sound log likelihood. That led to the two methods, flow noise and Flow-SDE.
Let's talk about flow noise first. How does that one work?
Okay, flow noise tackles it by modeling the denoising process itself as a sort of mini MDP, a one-layer Markov decision process.
One layer, okay. And the randomness.
It comes from adding a learnable noise network. So alongside the main network predicting the velocity for the flow, they train a separate small network that predicts noise, which gets added during the denoising steps.
Interesting. So the noise isn't fixed, it's parameterized and learned.
Yes. And it's learned jointly with the main policy network during RL fine-tuning. But here's a neat trick. Once training is done, you just discard that noise network.
So for inference, when the robot is actually running, it goes back to being deterministic and fast.
Exactly. But during training, because you have this sequence of noisy intermediate actions generated by the flow and the added noise, you can calculate the log likelihood of that entire sequence.
Not just the final action, but the probability of the whole path from noise to action.
Right. And the gradient of that joint log likelihood turns out to be exactly what you need for the policy update. It makes the intractable problem tractable by focusing on the process, not just the end result.
Clever. Okay, so that's flow noise.
Right.
What about the other approach, Flow-SDE?
Flow-SDE takes a different route. Instead of a learnable noise network, it uses a known mathematical connection between deterministic ODEs, ordinary differential equations, and related SDEs, stochastic differential equations.
So it converts the deterministic denoising ODE into an equivalent stochastic one.
Basically, yes. It introduces noise in a principled way that preserves the essential properties of the original flow, but now the process is inherently random. This uses a fixed noise schedule, not learned noise.
Okay, fixed noise schedule.
Yeah.
But introducing stochasticity into the generation process, does that change the structure? You mentioned flow noise was a one-layer MDP.
It does. Because the SDE transition is now part of generating the action at each environment step, Flow-SDE requires framing things as a two-layer MDP.
Two layers. How does that work?
You have the outer loop, the outer MDP, which is the standard Asian environment interaction. Observe state, generate action, get reward, new state. But then you have an inner loop, the inner MDP, which represents the SDE-based denoising process itself. The state in this combined MDP now includes both the environment observation and the current state of the action being denoised.
Okay. I can see how that works conceptually, but it sounds like it could dramatically slow down training.
Yeah.
If you have, say, 50 or 100 denoising steps inside each single step the robot takes in the world.
That's exactly the potential problem. Your effective horizon blows up, making each training update much more computationally expensive.
So how did they get around that? Did they just throw massive compute at it?
No, they came up with another smart optimization, hybrid ODE-SDE sampling.
Hybrid sampling.
Yeah. Instead of running the full SDE for all denoising steps within an environment step, which would be slow, they do something clever. For most of the denoising steps, they just use the fast deterministic ODE updates.
Okay.
But for just one randomly chosen step in that denoising sequence, they apply the stochastic SDE transition.
So you get just enough stochasticity injected to make the log likelihood calculations work for the RL update, but you keep most of the computation cheap using the deterministic ODE.
Exactly. It's a trade-off. You get the mathematical rigor needed for the policy gradient, but you drastically cut down the computational overhead compared to a full two-layer SDE rollout. Made large-scale experiments feasible.
That makes sense. It's a very practical solution. Okay, so we have these two methods. Let's talk results. How well did RL actually perform? You mentioned Libero earlier.
Right. Libero is a great benchmark, especially for testing few-shot learning and lifelong learning capabilities. They specifically tested starting from very limited SFT data.
How limited?
Like only 58 expert trajectories for arrow and just 40 for arrows. Really minimal supervision.
And with that little starting data, how did Terrell do?
The improvement was stark. For arrows, the success rate jumped from about 57-58% with just SFT up to nearly 98% using flow noise for RL fine-tuning.
Wow. And for error?
Similar story. It went from roughly 77% success after SFT to over 98% with flow noise. It shows how effectively RL can build on that initial imperfect SFT policy.
And you highlighted the Libero long result earlier.
Yeah, that one's really telling. It's a harder, longer horizon task. The few-shot SFT overhaul only got about 44% success. Pretty poor.
Okay.
But after RL fine-tuning, it reached 94% success.
Which you said was actually better than a model trained with SFT on the full data set.
Exactly. The full data set SFT model topped out around 92.4%. So RL, even starting with very little data, learned a more robust and capable policy through interaction than just seeing more demonstrations ever achieved. That's a powerful statement about RL's value.
Definitely. What about scaling? Did it hold up in more complex, larger scale environments?
Yes, they tested that on ManiSkill, specifically the multitask setup. This involves a huge number of pick-and-place variations over 4,300 combinations running in hundreds of parallel environments.
A real stress test for generalization and parallel training.
For sure. And RL delivered there too. Aru's success rate went from about 41.6% to 85.7%.
Doubled it, roughly.
Pretty much. And RL went from 40.1% to 84.8%. So it confirms the framework can handle large-scale, complex, multitask RL for these continuous action robots.
They also mentioned simpler benchmark games.
Yep, strong gains there too. About a 20% absolute jump in success rate for both models on simpler after RL fine-tuning. So consistent improvements across different benchmarks.
Okay, the performance gains are undeniable. Let's dive into some of the finer technical details and ablation studies they ran. What did they find when comparing, say, different RL algorithms? They focused on PPO, but did they look at others?
They did compare PPO with GRPO, Group Relative Policy Optimization, and PPO consistently came out on top.
In what way?
Both in terms of the final performance the policy reached and, maybe more importantly, training stability. For example, using Flow-SDE on Euro, PPO achieved a 96% success rate on Libero, whereas GRPO only got to 90%.
Any intuition why PPO would be better here?
The paper suggests PPO's clipping mechanism, which limits how much the policy can change in one update, likely provides crucial stability when you're dealing with these complex, iteratively generated action distributions from the flow models. It prevents updates from going haywire.
Makes sense. They also looked closely at the critic, the value function, right? Where you attach it seemed to matter.
Yes, and it depended on the specific model architecture, PAR versus HERS. Remember, the difference is how they incorporate the state information.
Right. In PO, the state goes into the action expert module later in the process.
Correct. So for HERS, the best critic, which they called expert, had to estimate the value by sort of averaging value predictions across the different steps of the noisy action denoising trajectory.
Okay, that sounds a bit complex. What about HERS?
In PERS, the state information gets merged much earlier inside the main vision language model VLM component before the action generation part really kicks in. So they could attach the critic there, $5.
And that earlier attachment point, $5, worked better.
Slightly, yes. It showed better performance metrics, lower value loss, higher explained variance. The thinking is that the VLM provides a cleaner, more stable representation of the state before all the noise from the action denoising process gets introduced.
So the critic gets a more reliable signal to learn from.
Exactly. A more stable value function generally leads to more stable and effective RL training overall.
Interesting nuance. Okay, let's compare the two main solutions directly. Flow noise versus Flow-SDE. Which one is better?
Well, it's a trade-off, as usual. In terms of pure peak performance, flow noise seemed to have a very slight edge.
How slight?
Like maybe 0.4% higher average success rate for Suro on Libero. Not huge, but measurable.
And why might that be?
The hypothesis is that the learnable noise parameters in flow noise offer just a little bit more flexibility and fine-grained control during optimization compared to the fixed noise schedule in Flow-SDE.
Okay, so flow noise for maybe squeezing out the absolute best performance. But what about efficiency? You mentioned Flow-SDE's hybrid sampling earlier.
And that's where Flow-SDE wins. Because flow noise needs to calculate that joint log likelihood over the entire denoising sequence. It has to essentially rerun the full denoising process during the backward pass for the gradient. That makes it computationally quite heavy.
About as heavy as a standard two-layer MDP approach without the hybrid trick.
Pretty much, yeah. Flow-SDE, however, with that hybrid ODE-SDE sampling where only one step is stochastic, it's much faster. They reported it cutting update times almost in half compared to the standard two-layer methods or flow noise.
So Flow-SDE gives you maybe slightly less peak performance, but significantly better training speed and efficiency.
That seems to be the trade-off. For large-scale training or practical deployment, Flow-SDE's speed advantage might be more important.
Got it. They also had a really important warning about hyperparameters, didn't they? Something about optimizing for the wrong thing.
Yes, this is a critical, practical insight for anyone trying this. You might naturally tune hyperparameters, like the number of denoising steps, or the action chunk size to get the best possible deterministic performance from the base flow model. Make the actions as smooth and accurate as possible.
That sounds like the right thing to do.
Right. But they found that settings optimized for deterministic fidelity can actually hurt RL fine-tuning.
Oh, so?
If you have too many denoising steps, high dollars, or maybe too little noise variance, it makes the RL process much harder and more unstable. The policy needs a certain amount of sort of wiggle room or exploration capability enabled by the noise and a reasonable number of steps to effectively learn and adapt during RL.
So optimizing purely for the smoothest deterministic action can make the policy too rigid to learn well from RL feedback.
That's the idea. There's a tension between deterministic accuracy and RL trainability. You need to find a balance.
One last technical point, fine-tuning the vision language model itself. Did jointly training the VLM using something like Libero alongside the action parts help?
Interestingly, on the Libero benchmark, it didn't seem to provide a clear benefit compared to just freezing the pre-trained VLM weights.
Really? So the massive VLM pre-training was good enough on its own for those tasks?
It seems so. For the types of variations present in Libero, the VLM's existing representations were apparently robust enough. And freezing the VLM is a big win. Computationally saves a lot of memory and speeds up training significantly.
Which is crucial for online RL, where you want fast iteration cycles.
Exactly. So for Libero, at least, freezing the VLM was the more practical choice.
Okay, so wrapping up, RL seems like a really foundational piece of work. It cracked that tough log likelihood problem for flow-based VLAs.
Absolutely. It lets these powerful PACES models finally leverage online RL, leading to really dramatic improvements in performance and generalization, especially when starting from limited data.
And they released the code and models open source, which is great for the community.
Always good to see. But, looking at the results, particularly the discussion around out-of-distribution or ODE scenarios, there's a lingering question.
What's that?
Well, RL massively boosted performance on tasks similar to the training distribution, but the gains on genuinely ODE tasks, where maybe the visual appearance or the objects or the task semantics really shifted, those gains were more limited.
And you mentioned freezing. The VLM was efficient, but maybe contributed to that?
That's part of the hypothesis. If the VLM's features aren't adapting during RL because it's frozen, it might struggle more when faced with significant distribution shifts.
So here's the thought to leave you with, especially if you're working in this area. We often freeze the VLM during RL fine-tuning for efficiency, right? It saves compute, saves memory.
It's often a practical necessity for large models.
But if that limits ODE generalization, how can we design the RL stage, maybe the reward structure, or perhaps doing RL in the VLM's latent space somehow to encourage or implicitly force the VLM's representations to adapt to new environments or ODE data, without having to pay the full, massive cost of end-to-end fine-tuning the whole VLM?
Yeah, how do you get the VLM to learn about the new stuff relevant for the RL task, even while most of its weights are frozen? That's a really interesting challenge for future work. How do you get that adaptability without sacrificing the efficiency?
Something to think about. That really digs into the core of building truly robust and adaptable AI agents.